Okie dokie, we're back with lecture number 3, talking about collections. We ended on slide number 48, or 58? 58. So just to bring you up to speed what we were talking about. The concept of the collection in terms of what how it's used as a data structure, the terminology associated with it, the mention of the Java API that works with collections, that includes items for stacks and queues and lists. All of these items fall into the list category. I believe I was talking about the stack actually a lot in terms of the operations on the stack, the push, the pop, the peek, common methods that would be created inside of a class structure that would represent the concept. Looked at the concept of inheritance and object orientation, and looking at the UML diagram of an animal and how we get a reptile, a bird, and a mammal from that, and how that kind of goes down into another hierarchy of different types of specialized mammals and birds and reptiles, which is sort of the similar concept that we have with the data structures in the collection. So we have a collection, then we have a list, and then we have different types of lists that might be associated with it. Concept of polymorphism, as it's enabled in a language to support our data structures. The concept of a generic type, specific types, looked at Java interfaces, the stack abstract data type, which is what ADT stands for. Didn't go through the implementation of it. I'm going to save that for a future lecture. We'll look at Java and we apply it to Java language. And then looked at the concept of the stack in terms of evaluating the expression, what the stack was actually used for as a data structure. And the concept of the linked stack, also looked at that. The theme of the next lecture is actually linked structures. So linked like a linked list. And so I'm going to save a little bit of discussion on that for the next lecture. Let's see. We got as far as looking at exceptions and exception handling in the language, managing capacity, looking at are we filling an array, are we filling a structure. One of the interesting things is when you start looking at the concept of a data structure is the capacity. And do you want to fix the capacity up front, having it by using a structure that's going to limit the capacity, or do you want to make the structure grow unlimited? And that's one of the implementation issues that you have to think about in terms of the underlying structure that you're going to build. And if you use a construct like an array as an example, you're going to be fixing and limiting the number of elements. If you use something like pointers and dynamic memory allocation, then you can make it unlimited. So how basically are we going to create the numbers of the cells? How many cells are there going to be? Its capacity. And its limitations, and can you throw an exception when it gets full, testing to see if the capacity has been reached. And then also looked at the concept of exceptions, problems that arise and how they're caught and dealt with in terms of the Java interface. And Java is a nice language because it has automatic exception handling built in. We can catch all sorts of different exceptions. If you're not familiar with Java, don't worry about it. You don't actually have to do the assignments in Java. You can do them in C or C++. You want to be familiar with at least one programming language, however, in order for any of this stuff to make sense. Here's an example of the try statement with a try catch. So you're going to try, which basically means you're going to perform some statements, execute some statements, and then catch an exception that might exist. Let's see. We stopped about here, I think. The ArrayStack Class. So let's examine the concept of an array-based implementation of a stack, which is what an array-based stack is. We're going to compare this one with a linked list stack, which is going to be the theme of the next lecture. But in terms of the array, that's probably the easiest way to implement it. And in terms of the assignments, you can use arrays all you want. The only problem with arrays is that they're statically allocated, which means that size is fixed, which means we have to deal with the capacity issue. So we're looking at the following design decisions that need to be made. Maintaining an array of a generic reference may not be capable in a language that doesn't support it. So in most arrays, you have to give the array structure I hate to call it a structure. I don't want to call it a data structure. I think I'll call it a construct. You have to give the language construct a data type, integer, float, double, and you're stuck in terms of the implementation of that construct, you're stuck with only storing linked data types in that structure. If you went the other route and didn't do an array-based ArrayStack, you did something that was like using dynamic memory, you could potentially have a list of items that were all mixed and matched that weren't limited to one data type. So maintaining an array of a generic reference is kind of an interesting decision that's going to need to be made. The bottom of the stack is at index 0, perhaps, if you start out with array indexes. And then each one of the index values is going to have a particular value associated with the index. Elements of the stack are in the order, and they are contiguous, which means they're lined up one right after the other in terms of the array. An integer variable at the top stores the index of the next available slot in the array. So we're looking at the top and a starting point or a bottom or a 0, meaning at the beginning. This approach allows you to grow and shrink at the higher indexes. So you're adding from the beginning. So if you have an array, here's an array implementation of a stack of, we don't know how many, we're just going to say it has more than 7. Where we have 0 is going to be A, B, C, D, we're going to put we're going to add numbers to it from the bottom of the index, starting with 0. And we could definitely use like a for loop or something like that to populate this particular array. And the array implementation of the stack, the top value would be the index value of 4. So in here, in order to, which is one of the implementation issues associated with an array, we would have to go through each one of the items to see how many items were in there. We would have to go and sort each item. If we wanted to insert something into here, we would have to manually kind of move everything over one index value. But this is what's commonly referred to as an array stack index, an array created stack. And here's some source code that would be capable of creating it in Java. And as I mentioned before in the last lecture, I'm not going to go through all of the source code. Instead, I'm going to have some examples in a couple of weeks that are going to put all this stuff together, show it to you that way instead. But here you might notice you have a default capacity. So you're setting the capacity here of 100, which is important to note. And you can do this by implementing a class if you're in Java. If you're in C++, you could do it by using a structure or a union or a class. You can use a combination of classes and structures. A few more options in C++ than you do in Java. Java, you're limited to the class operation. And here's the class implementation, I should say. And here's a push operation example of creating a method called push, where you would push something, put something on, pop is to take something off. So the terminology associated with that. So here's a stack after pushing element E on. E went into element 4, so element 5 would be the next top. So it just incremented. So that's why it's referred to as a list structure, because the index is incremented by numbers starting with 0 going to the maximum capacity of this structure. So, well, -1. So the stack after pushing the element E onto it. And then the pop operation would be to pull it off. And when pulling it off, you're actually just removing the last element. So which makes it, meet the stack protocol. So a stack, you push it on and you take it off from the same end. And the opposite of that would be using both ends, and then you'd end it with a Q. So if you put it on this end and took it off this end, but you can't do that really easily with an array. So if you can imagine the possibility, it works great. Array implementations work nicely for stacks, and as I mentioned before last week, that the stack is normally of some sort of a particular length. It usually has a maximum length in most implementations, not all. There might be some cases in which you don't want a maximum length. And you're only working with one end, which kind of makes the array implementation easy, simple, because you don't have to sort everything. If you're working with both ends, let's say you turn this into a queue, and you are taking it off, last one in, first one out, and you are putting them in, you keep having to move everything over if you kept putting it this way, which very inefficient, going back to the concept of algorithms and the efficiency, but run very slowly because you have to keep reorganizing this. So an array queue implementation doesn't work as well as a stack. So most people would consider an array stack, sort of a better approach, but that might not be a good solution to the problem you're trying to solve. So, if you're going to use an array, you can use it quite efficiently with an array stack. The peek operation is the one that's going to go through the array and look for a particular item. Other operations that might be associated with it, the size operation is implied as a matter of returning the count, which is you're going to go through and you say, is it empty or does it have a value? It has a value. Then increment a counter to that with a for loop. And the is empty operation returning true if the count is equal to 0 and false if it's not. So knowing whether or not the array actually is full or empty is something that is an issue when, not an issue, a design feature when you're trying to figure out how you're going to create a stack essentially for use. The toString operation, if concatenated to the string, might make the results to a string, for each one of the stack elements to print it to the standard I/O. So in terms of the analysis of the stack operation, going back to Chapter 2, the analysis of these algorithms that we're using, and the algorithm is nothing more than the technique that we're implementing this structure with. Because the stack operations, they all work on one end of the collection, they're generally efficient, which means, going back to what I said about arrays, it's efficient. You're only working on one end. If you're working on the multiple ends, not efficient for this particular thing. So the push and the pop operations of the array implementation are going to be big O to only one execution. So otherwise, you're going to also have any other operations would also have the same runtime actually. So it becomes a very simple level, efficient type of structure, which works out quite nicely. So now we're going to see when it doesn't work out quite nicely. So that was essentially lecture number 3 that went into the concept of collections. Talked about lists, if you remember. Talked about the queues. Talked about the stacks. Lecture number 4, chapter number 4, is another long one, so I'm going to cover about half of it. I'll probably get through about slide 50 or so. And what this is concerned with is the linked structure versus the array structure. So we're comparing linked with array. And most, 99.9% of all programming languages out there support arrays. It's a built-in structure. It's not something that you have to create. Links depends on the language. Some languages actually support, and Java does support, a built-in API that's going to give you a linked structure. Versus some other languages like C, C++, where you're going to actually have to create it yourself using new and delete and dynamic memory allocation. So the chapter itself, we're going to describe and use the references to create linked structures. I'll show you how that's done from a non-programming implementation, but from a theory, a concept-based. And then compare the linked structures to the array-based structures. And you'll see how the linked structure is a bit more efficient for certain things outside of the stack. The array is going to actually be your best implementation approach. And then we'll look at exploring the techniques of managing the linked structure itself, some of the issues associated with it, discussing the need to separate the node from the linked structure itself, and I'll talk about the concept of a node in a few minutes. And the implementation of the stack collection using a linked list, which one of your assignments, I believe, will have you work with linked structures. So to give you some practice with it. References as links. There's many different ways to implement a collection, as we've seen so far. Hopefully you've walked away at least with the concept that collections are an accumulation of different implementations. So, Chapter 3, we explored the array-based implementation of a stack. We just looked at it a few minutes ago, so it wasn't that long ago. Now, the linked structure uses an object reference variable to one object, to another object, to another object, instead of what's called an indexed structure. So the list, there's a really good reason why they call that array indexes. Index because it's an indexed structure in terms of the concept. Linked lists are non-indexed. There's no index. There's no numbering, there's no ordering system. Instead, each object has a reference to another object. So you can recall that the object reference, the variable stores the address of the object. In that sense, the object is a pointer to an object, which is why in C and C++, usually you learn about linked list when you start learning about new and delete and how to create dynamic memory, memory allocation, because you're really working with pointers is what you're working with. But the interesting thing about a linked list, if you think about the concept, is there is no list. There's no list, really. It's just a bunch of objects and pointers to other objects, which makes it vulnerable. You can't lose half of an array stack. The array is a structure that's kept together by a common base, which is that index. Index never goes away. So you don't have an index, all you have a bunch of memory. It's easy. It's not quite as strong, not quite as secure as a data structure, because it's easy to cut it in half and lose half the list. It's easy because it's not managed or it's not stored all in one concept. It's all over the place. It's loose. It's free. So here's a figure. Here's the object reference variable pointing to an object. Flexibility. So we have pros and cons that I'm going to go over. One of the definite pros to this is that we can have a list that contains non-liked items. They're just references to memory objects. So a float can have a reference to a string, it can have a reference to something else, that has a reference to something else. So, and it depends on how we implement it as to what we're capable of actually storing in the list. So we have what's called a self-referential object. So a person object, for instance, could contain a reference variable to another person object. So all the people could know about each other. That's why we take attendance, I guess. So we figure out all the people. And then, if the attendance list, well, that's an array list, really. And I would call the array list, actually it's a stack, because each person who signs an attendance list usually puts their name underneath the last person. Unless you leave room at the top and the bottom, but we don't normally push on or pop off. We just essentially just list, which is why they call it an attendance list. No need to implement that using a linked structure. But if we didn't have that, we could have people that knew about other people that knew about other people, and we have like Facebook. Facebook is a linked structure. If you think of the concept, every time you have a friend, one person who has a link to another account, that's a linked structure in theory. So the person, if we were to implement it in those people in the Java class, this is about as far as we've gotten so far. So you're up to speed already on this concept. So if we created an object, we would have a public class person as an example. It would have a name and an address, and then we might have person next, which is going to be a link to another person object, which is how we could keep track of people. And the interesting thing about objects in a linked list environment is that they could be any object, as I mentioned before. So people like to get really abstract with this, and they will create a list, and then they'll create a node, and make the node a generic object. Because people, well, what is this list storing? It's a list of people. Then we would have people objects. Or it's a list of plants, so we have plant objects, or it's a list of classes or something. The more generic form of that is called the node. So a node is just an object that has like no name in particular. It's just a node. So nodes hold things. There are placeholders for people, placeholders for plants, classes, whatever we want to put there. And so the linked list, this type is a reference that can be used to form what's called a linked list. And again, it's another list, but there's no index. It's not an index, so it's a linked, in which one object refers to the next, which refers to the next, which refers to the next, and creates with the common linked list structure we see in C or C++. Each object as a list is often generically called a node. That's where that node vocabulary came from, which I just talked about a few seconds ago. So the linked list is also referred to as a dynamic data structure versus a static one. So the array is static because it doesn't grow. and that's just the terminology that you're supposed to remember out of this. And dynamic can grow, and it can also shrink as needed. So it gets big, it gets small, and unlike the array whose size is static or fixed. So Java objects are created dynamically when they are instantiated, and Java actually supports the concept of the linked list without the programmer having to create it. Which is why if you know C or C++, you can get by just fine in this class. No problemo. Only problem is you're going to do more work. If you're doing this in C++ or C, you're creating a linked list. And you are creating nodes in a tree, and you're doing the whole thing manually. If you're doing this in Java, and I think as soon as next week I'm going to bring in the examples for it, then you're just using the API, and you're making a new object instance of a linked list, and you're adding nodes, and you're basically running methods from an object that already is created for you, which isn't too bad. So here's our linked list. We have the front, and then we have the end. A linked list is good for queues. Why would you bother creating a linked list for a stack? You don't really need to. You could probably use an array for that. Or if you had a stack that needed to grow dynamically and you didn't know how many members were going to be part of that stack list, then you could use a linked list. In fact, you have many choices. You could essentially have any data structure you want hold any data that you want. There's no rule or law that says you have to use an array list or you have to use a linked list for something. It's just going back to the Chapter 2 concept of efficiency. Some structures are just more efficient for the application. And that's more of a skill in terms of practice, knowing after when you're creating a new application, what structure am I going to use for this? What data structure am I going to use? And it's your choice. And then some programmers might have a tendency to go towards what they know and what they're familiar with. They may not necessarily be the correct choice for the solution, which might make the program run slower, not as efficient as the correct choice would have. So nonlinear structure. Linked list, as the name implies, is a linear structure, but it's flexible. It's not fixed. So the object references also allow us to create nonlinear structures such as hierarchies and graphs. So if you think of the concept, if you have just objects pointing to objects, do they need to do it in a linear fashion? No. You can have one object point to another object, who points down here to another object, points over here to another object, and that would be nonlinear. So it can be used for both, linear and nonlinear. If you used it for linear, you'd basically be creating an array-based implementation without using arrays. Here's an example of a complex linked structure where we've got, looks sort of like a map actually. And I'm going to talk about maps later, trees later. These are all classic data structures that you run into. It's just different ways of representing in a non-linear fashion the data. If you had, actually, this could be sort of a sideways family tree actually, or a tree. I always think of family trees when I think of trees, which is why I said that. Because you have this guy who leads to this guy, who leads to this guy. Oops, stops. Okay, so we have this guy who leads to this guy, who leads to this guy, also leads to this guy. So we have branches and directions, which kind of lends itself to a map as well as a tree structure. So usually you see trees going from the top to down in some sort of a linear tree progression where each branch doesn't terminate, it kind of goes to a leaf. We have that hierarchy of a root to leaf, which is why they call it a tree, versus a map, which doesn't necessarily have clear paths that go all the way through. It's kind of like maps of neighborhoods. Sometimes we have dead-end streets, or we have streets that don't take us to the same location as other streets might. They don't all go to the same point. They're shorter, and they're different routes. So managing linked lists. The reference to the linked list must be carefully managed to maintain the integrity of the structure. That's what the problem comes in. When you lose the reference, only one, you've lost the structure. Very vulnerable to mistakes. So you have to have special care that must be taken to ensure that every entry point in the list is maintained properly. So the overhead of the particular implementation is making sure that the references are correct and you're not referencing to something that doesn't exist anymore. is if, let's say for example, you removed something and there's still a reference for it, you've got like a black hole. You've got a path where this guy's going to come down to here, and then this is not here anymore. Uh-oh. So now you've lost everything that maybe have been attached, maybe have been referenced by this that's gone. And you can lose chunks of the entire structure easily by messing up one reference, which makes it vulnerable. If you mess up one reference, you don't have references, but if you mess up one thing in an array, it's only that one item. Everything else is not affected by it because you have the common index that keeps it all together. So in order, the order in which certain steps are taken is important. If you're going to remove a link to put a link back on, you want to make sure you attach the link to another object before you remove it, so you can keep the link and the reference correct. Considering the insert and deleting of the nodes is in various positions within the list is also an issue. The operations aren't consistently the same. As an example, if you have a head node that's indicated by something, an insertion or a deletion of something right there is going to be different than something that's further down, or maybe the other end that has a tail reference or null reference. It might have a different operation. So you always have to check to see where you are in the link structure to see what operations might be legal or how you're going to actually perform the operation, which makes the operations inconsistent. So, and here's the example here of inserting a node at the front of the link list. A little different than inserting it in the middle. So, inserting a node at the front of the link list here, where we have one, and then we have another node that we're going to put here, and it means we got to move this guy over, which means we got to say front doesn't go to here, front goes to here now. But we don't have a front right here or right here. This is sort of like if we were adding to the end. To add to the end is different from adding to the middle of the link. Same thing as the front. Because usually we have some sort of keyword or some sort of indicator or something to say that this is the start or this is the end. Because this is a self-contained list, and we never really know how long it is. So we refer to words, special nodes that mark the beginning and the end. It's kind of like a train if you think about it. The front of the train always has like what they call that? The house, the cab, or the engineering, where they steer the train. And we have all the boxes that are connected on the train. So if we put a box in, no problem. Anywhere, it's all the same, but right next to the front, that has special needs for the connection or something. The connection is going to be different, which is similar to what ends up with the linked list. So inserting a node in the middle of the linked list, a little different. You just break these two apart. You say this guy is equal to this guy, which is equal to this guy. Which you don't have a front anymore to think about, or a tail if you're on this end. You just have to figure out who the current is and then move it in. So usually you see the words current, node to represent these objects, which are generic terms essentially. Deleting the first node in the linked list. We have a node here that we're going to delete, and we're going to make this one the first one instead. Slightly different, we just make front equal to the second one instead of the first one. And usually by rule of thumb you want to make the new connection before you get rid of the old connection. So, and depending upon what language you're working with, if you're doing this in C++, you're creating your own method to do the insert and to do the delete. And you have to make sure that you don't have you're not creating inaccessible objects. So normally you have another node that you're using as a temp node that you're doing everything to, and then you're keeping the reference to the old one so you can delete the old one. Otherwise what ends up happening is, although you've deleted it, it's not in the structure anymore. It's still allocated. So you caused a memory leak. Here's a deleting an interior node from the linked list. We have the previous, we have the current. And so if we delete this current one, then this one is going to go to this one. Just bypass it. So what you don't want to do is lose one of these. If you do that, then half the structure is gone. which is very common actually when people write these by hand. Luckily for you with Java, you don't have to do this by hand. You just say delete, insert. You just use it like it's any other built-in data structure. Elements without links. We can have tons of elements without links, and we can add them in easily. Can't have that in an array. In an array, you've got 1 through 100 or so elements. If it's not in the array, it's not in the array. In a linked structure, you can have objects all over the place and mix and match objects. And put new objects in, take new objects out. A lot more flexible. Problem with self-referential objects is that they must know they are part of the list. So unless you don't tell them that they're part of the list and you make them, part of another list, you can have multiple different types of lists and then have the lists come together somehow. Combine the lists, sort the lists. So it's a lot more flexible. A better approach is to manage the separate lists of nodes and also the references that are stored in the list. So you can have a temp list, you can have list 1, 2, 3, different versions of the list. It's all still the same memory objects, but you're just changing the list around, which is why in C++ you do this with pointers. Because you have pointer variables, and the pointer variables, you can have tons of pointer variables. It doesn't take up any memory. It's just pointing to the same memory. You can take the whole list, resort the pointer variables, and then use the new list. And then it's an instant resorts, much faster than taking this and copying it here and copying it here and copying and resorting something, which makes it an efficient structure. You can have multiple different sets of lists on the same objects, in different orders, which makes it efficient as well. So the list is managed by using the same techniques, and the objects stored in the list need no special implementation to be part of a list. They're just an object. Any node can be a part of any list, which makes it more generic. Generic list collection can be used to store any kind of object, which in object-oriented programming makes a lot of sense in terms of your capabilities. So here we're using a separate node object to store the linked elements. And this is where we come into the concept of having nodes that are put into trees, or having nodes that are put into lists. So in C++, when they teach you about how to create a linked list, you create a list, and you create a node, and you put the nodes in the list. So you actually have two structures instead of one that you're working with. Java, it's actually just one by abstraction. You can actually separate it out if you wanted to. So here we're using separate node objects to store the linked elements, and the nodes are part of the list. So we have two separates. And in C++ and Java, as I mentioned before, you can do this all by implementing it in classes, or you can have structures. But these can be represented in any type of fashion that might be efficient or inefficient. Sentinel nodes, so they're variations on the implementation of the linked list, and might be useful for different particular situations, as I mentioned already. One such is the use of a Sentinel node or dummy nodes on either end of the list. So you can pack it with dummy nodes to stack the list, make room for new elements in the list, or to show elements that might be missing in the list. So you can kind of use it abstractly as placeholders, or as front, end, tail, dual, a lot of different terminologies for it. This practice eliminates the special case of inserting or deleting the first or the last node, because you have something already there, and it makes all of the operations consistent, because the first never gets changed. It's always the first, and then we have a dummy next to it, and then we have the list. So we keep track of it. It makes insertion anywhere in the list equal to any other insertion anywhere in the list. So it makes the structure a little bit easier abstractly. We also have the doubly linked list to make a double list out of it. Another useful variation. It's called the doubly or double linked list. So in a doubly linked list, each node has a reference to both the next and the previous nodes. So a single linked list, and imagine this like kind of like a chain link fence or a chain link kind of structure. So single has one claw that comes from one node to another and grabs it. So it knows about the person in front of them, usually, the next. In a doubly, it knows about the next. It also knows about the previous. So it holds on both ends instead of just one end. Makes it a stronger link, a little bit more reliable. Also makes it so that you can traverse it in both directions. So instead of using it like one directional type of search mode, think of the concept. You have node A, B, C, D, a bunch of nodes. All they know is next. You travel in one direction. You go from this node to this node to this node to this node. If you have a situation where, say, you don't have a linear list, and you want to go, and you're here, and you want to go here, and you want to go here, you need a doubly linked list, because you need to know about this guy and this guy, because he's not necessarily linear. So you can actually have a triple, quadruple. You can have any kind of, and this is where you get into the tree structures, where you can have any number of branches. This node's got 14 branches. Got 14 links, references to 14 different branches. So then the concept essentially is the same. It's universal. It's all a linked structure, but you have multiple links going to multiple directions for multiple purposes. In terms of the list, we call it a doubly link because we've got the forward and we got the previous, next and previous, which is what we're concerned with a list. In other types of structures, we have different names to kind of signify the tree, what we're doing with that. So it makes traversing the list easier in a doubly kind of fashion for a list, because we can go this way and then we can also go this way. We can go backwards and forwards. Makes it more efficient, so we don't have to follow it to the end. And here's our little efficiency here, where we go from the front of the list to the rear of the list. If we have a next, 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 that's the singly. The doubly is the previous, 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 previous. So we could go back into here and then turn around, go this way. Here, turn around, go this way. We don't have to actually go through the entire list to get back. So to follow it backwards. So implementing a stack with links, it's possible. You can do it. It's easier to do it with an array, in my own personal opinion. So we looked at, we can use a linked list to implement the stack collection from Chapter 3, what we just looked at a few minutes ago, the array-based stack. However, we'll need to create a linear node class to represent a node in the list. So it's a little bit more work. We just can't just create the array and put everything inside of it and call it a stack. So our linear node is going to be our generic node that's going to keep track of our next, our next, our next. And it's a reference to the next node in the list. We also have something that we're going to store. So our linear node has an element, it's holding something, because we have items that we're going to need to hold in this list. And then we have next, next item, next item. So in terms of our implementation, we create the node itself, and we have operations to go to the next, get next, to go and to delete an item, to insert an item, and all the different operations that you might imagine. So I'm not going to go through this code today, but I will skip to this operation here. So this is what it would essentially look like. So a linked implementation of a stack collection sort of looks like our array, except for we don't have index numbers for each one. Instead, we just have the top, and then we have the top of the stack, and then, which is all we're concerned with, because we're adding on to the top and we're taking away from the top. And we have the push and the pop operations coming off of the top. We have no end. We just have null back there. And so we add on and we stack them up, one linking to another. In a stacked implementation of a linked list, we don't need to do it doubly. Singly is perfectly fine for that purpose, because we're only going in one direction. We're not actually trying to traverse it in multiple directions. So our linked stack, in terms of its implementation, it's very similar in terms of the other examples that we've looked at so far, where we're implementing, let's say here's our list. Our count would be 4, because we have 4 nodes that are created. We can increment a count. Each one of the nodes could actually keep track of our count for us, which is a pretty common kind of thing, because each node knows about the next node, about the next node, about the next node. So as we're as we're pushing items onto the stack, we can be incrementing a counter that's shared by all nodes. And we can as we pop things off, we decrement the counter. And so at any one moment of time, we can come out with the count quite easily. And the push operation puts something on, and here's what I was talking about here, taking a counter and incrementing it, so counter plus plus. So we create a new node, set the current node to point to the new node, and then increment the counter, essentially, which is how we're doing the pop. Excuse me, the push. So linked list after the push operation here, we're going to push E on. Before we had D, C, B, A, so now we have E on the top, and the count is now 5. In any one moment, we can ask any of the nodes what the count is. The nodes should know. And if you're taking the Java class, that would be a class level variable using static that we would use to implement that. But as we get further, I'll show you another example that uses a different technique as well. The the pop operation to pull something off. We pulled off the E. And I believe in this particular example, we should have had here we got the count minus minus down here. So it's just a common variable that we're keeping among all the nodes to keep track of who's on there and who's not. So we take the D off, and we have the rest of E off, and we have the rest of the stack here. Now it's down to 4. So other operations that might be performed on a linked stack using a linked implementation to peek. So peek is sort of like a find, a search and a find. So the operation is implemented by returning a reference to the top. Peek essentially is only looking at the top element because we're only pulling off of the top. So we're saying, peek, what's the value of 5? Or no, D actually is the value. It was called in characters. And then we can also peek to see if it's empty. So the is empty. And these are the same operations that we saw with the array implementation. So hopefully you're starting to get the impression the operations are the same. They're just implemented differently for the different type of data structure that we're designing. So the is empty operation returns true if the count of the element is 0, otherwise it's false, just the same way as we saw with the array-based implementation. Size operation simply returns the count of the elements, which is kind of interesting because do you necessarily have to go through and count each one of the elements? No. If you had an array stack created and you had 100 elements, you said this array is a size 100, as we saw in the previous example, you'd actually have to create like a for loop to go through and say, is there something in this one? Is there something in this one? All the way through 100 times. Come out and do a manual count. In a linked list implementation, all you have to do is have a variable that's shared by the objects, all of the objects, just like the count. And at any one moment of time, you just say, what's the count? 5. So in terms of sophisticated operations on the structure, linked list is easier. So arrays, if you're concerned with the count, if you're concerned with the number of elements and the dynamic growth of it, not such a good structure. If you're not concerned with that, more efficient than the linked list. So it's kind of a toss-up when you want to use one or the other. So if you want an easy manipulation on the operation, as another example, if you want to insert in the middle of the list, this linked list is easier. If the array is only going to be used for a pure, authentic stack, where you're going to load it up, you're going to take it down, load it up, take it down, then it's perfect. An array, there's nothing wrong with an array-based implementation. So sometimes I see programmers that put together linked list structures for simple operations like that. And you're wondering, why did I just create an array for that? Because somebody drilled into their heads that arrays were bad and that, everything has to be a linked list. No, or maybe they think a linked list, makes them look more sophisticated as a programmer. I don't know. It is ridiculous if it's overkill. And then plus that linked list is going to run slower than it would if you just created an array for that. But, you can argue the opposite and say, well, if I'm inserting in the middle, if I'm concerned about the counts, if I'm not just loading it up, unloading it, loading it up, unloading it, then maybe I want to use a linked list. A little bit more flexible in terms of the operations. Allows you to provide more operations. So, two-string operations implemented simply by traversing the linked list and converting it to a string. So the analysis of the stack operation, we just looked at the analysis of the array-based one. And this should hopefully look familiar. It's the same. It's the same efficiency. It's just more flexible. And it provides a little bit more utility, a little bit more operations. But the efficiency of it, if implemented the same, should be the same. So, like our ArrayStack operation, linked stacked operations work on one end of the collection and are generally efficient. It's because it's working on one end do we have the pop and the push taking up the same O notation, big O time. Otherwise, the operation is also going to, it's the operation, so it tells you essentially, it doesn't really matter how you implement it. It's the stack operation that's giving us the efficiency of that particular algorithm, and it's the stack implementation itself that's efficient or not efficient for the particular application we're working on. So as a data structure, stacks in general are the most efficient. So you don't want to use if you can use a stack, use a stack. You don't want to use a queue when you can use a stack. It's easier. It's faster in terms of the efficiency of the algorithm. So using a stack, traversing a maze. Classic use of a stack is to keep track of alternative choices in maze traversal and other trial and error type of algorithms. As an example, let's say for example the traveling salesperson algorithm, where it's going through a bunch of routes and it has to keep track of, if I go this way, it's kind of like when you get in your car and you decide you're going to drive home from I-2, which way you're going to go. In your mind, you think, there's a shortest route, hopefully. But maybe the shortest route's got freeway. Maybe that freeway is going to be bumper to bumper time of day or something. So you can actually use a stack to load up all the different routes. I know you're going to do this in your head as you drive out of here. Create a stack for each one of the different routes you could possibly take. And instantly you're going to know this has got 5 streets, this has only got 1 street, it's got 10 stops, because maybe you're counting stops, streets, traffic, who knows. And you can use it to minimize, to find which one is the shortest one. You can use it to find, as an example, which one has the most side streets, the fewer stop signs. And you can actually use it as a, people do this all the time as well. You take one route and you decide, oh, I don't like this route anymore. I'm going to go to the other route. So you stop on this route, you take a slight detour, and you pick up another route, depending upon where you're at. So it's kind of the use of a stack, actually, in terms of a real-life example. So using a stack in this way simulates recursion, actually. Now, recursion is when a method calls itself, either directly or indirectly. One instruction is going to call another instruction, which is going to call another instruction, which is going to call another instruction. That's going to send you in the right direction, hopefully. So it could be considered a form of recursion. Runtime environments keep track of method calls by placing an activation record for each one of the called methods on a runtime stack. I believe I mentioned this last time in terms of the original implementation of this. This structure came about by runtime environments, if you think of it. So you've got a runtime environment from an operating system. Maybe it's a JVM, maybe it's Windows, the Mac. And you've got what's called activation records, which are nothing more than instruction sets. And you've got hundreds of them. What do? You load them up and you run through them all, and then you load up more. And then you run through them and you load up more. Think of it sort of like a to-do list. But you have to do the to-do list in order. So you write something down and you go through the list and you check them off as you do them, which is a stack implementation. It's a stack, essentially. You put them on in one order, you take them off in one end, usually. Unless you're the type of person who makes a list and then picks and chooses. That would violate the stack rules. So when a method completes the execution, it's popped off the stack and the control returns to the method that called it, which is kind of like how the activation records work. One activation record is going to create another, it's going to create another, it's going to create another. And in order to execute them, you've got to kind of run them in that same order. And then when they're all done, they're done. They're off the stack. And then you load more instructions on the stack and then you run through them off the stack. Which is how activation records on the top of the stack work. because one's going to call another, is going to call another. So you're actually running them in reverse order. So in this manner we can traverse the maze by trial and error by using a stack to keep track of the moves, and have not been tried yet. Actually, you can do this for checkers games, chess games, mazes, going through all sorts of different calculations. You just keep track of all the moves. In fact, genius chess players do this. They know how many. They look and they go, well, if I do this, you're going to win. No, if I do this move, I'm going to win. Or, because they already know it can calculate all the different possible moves that can be done from that. Well, it's a stack application. So they just have a really big stack in their head. Sometimes, I don't know. And I guess it's like counting cards too, but it's a little different. That one is using a different type of algorithm because there's only so many moves you can do on a chess game. Or and you only have one or two of each character or something. So the maze class, you can create a class called maze, and you can have implementation of this to keep track of. And here's, you can create a grid, and then keep track of the coordinates. Use a couple of arrays for that if you wanted to. And then traverse through the number of steps it would take you to get from point A to point B on all of the different paths. Put them all in a stack, separate stack for each one of them, and then see which one you want to take. Maybe the one with the fewest number of steps, perhaps, might be a good solution to that problem. This, believe it or not, is actual executed source code. It comes from the textbook, and you can cut and paste it off of the out of the book or out of the lecture, actually, and run it, and it should compile for you. It doesn't need any external libraries at all. It's all written inside of it. So if you created that class to keep track of the stack in terms of the maze class, you would write another structure called a maze search class that would be used to search through the structure, the mazes themselves, and select one and perform operations on the maze itself. So the maze search would have a position class to say, well, where am I in the maze, and how am I going to go from point A to point B? Actually, I'm going to kind of skip through this code. So let's talk about the Java implementation for a second. And next week I'm going to have some source code examples that I have to put them actually out on vhacker.com. They're not out there yet. That are going to be written in Java that are going to use these particular APIs. So the collection framework is defined by the stack class, and similar operations as we've seen in the lecture set. In fact, they're similar to ones that you would implement if you were writing this in C or C++. It is derived from vector, so that's where the hierarchy, in terms of the class hierarchy. Therefore, it has some of the characteristics that are not appropriate for a pure stack if we use that one. Otherwise, we can go into util. Most of the ones we're going to use for this class are going to be in the Java util. So some people go Java to import Java util dot with an asterisk to say, give me everything. Or you can go to the stack level, and that's one of the ones that we're looking at in terms of this class. And this is included. You don't have to install anything outside of the JDK. It's already included for you. You should be able to get the util standard package. So the class has been around since the original version of Java, and it has been retrofitted to meld with the collections framework. And the collections framework has more than just stacks in it, as we've seen. So if we take a look at a UML description of this util stack class, kind of see that. Maybe I can make this a little bigger. There we go. A little bigger here. So what we're primarily interested in are the operations for clonable, collection, list, serializable. And this is where I'm going to show you, because it doesn't make very much sense to show you pictures of this. That's why next week I'm going to come in with some examples, and we're going to see how to create stuff. So if you bring your computer next week, you can download and run through. I'll probably use Eclipse, actually, because that's what I'm using in the Java class. So if you're taking the Java class, this is going to come in handy, actually. But don't worry about it. I'll just go from everything from the beginning forward. So everything is being inherited from object, as we've kind of known already. And then we have abstract collection, which is essentially the big bucket of everything. As I mentioned before, stacks are part of collections, so are queues, so are lists in general. And then we're going to have our abstract list. And it kind of comes from vector, as I mentioned before, stack kind of comes from vector. Why they did this, I'm not sure, actually, because I would have branched it out a little differently. But in here, under the stack, we have our basic operations. And so what we can do, and these are interface classes that interface with the base class. So in Java, we've got kind of an interesting phenomena that occurs that we don't have in C++. So if you're new to Java, the concept of the interface gives us functionality and gives us, I want to say, multi-line inheritance, but it's technically, if you talk to the OO people, it's not really multi-line, but it does sort of give you multiple line inheritance. Rather than going one class to another class to another class, you can combine functionality by using interfaces. So most people are familiar with the concept of inheritance, where you have a class and you inherit it from another class, and inherit that from another class, and then that would be a single line. That's C++. We've got classes that are inherited from each other in a single kind of single linear kind of fashion. Java, same thing occurs, but then we have, and this is what's showing us over here, the interfaces. The interfaces add functionality from other classes as well to this particular class. So we have collection interface, list interface. I'll save clonable and serializable for next time, but the concept of creating a stack that's a collection, treating it like a collection, and then also treating it like a stack, and then treating it like a list and a collection, which does nothing more than give us multiple levels of functionality. So we can create a list and use it like a stack, and then also use it from a collection interface. And then the interface adds the methods that we implement in our particular structure that we're creating, our data structure that we're creating, that's going to hold all these data elements. So the purpose of the assignments for this course, and I'll talk about the first one in a few minutes, is to see if you can implement the concepts. You don't have to use Java. If you know a better way of doing it that you like to do, you can use that. But for the purposes of how I'm going to demonstrate it starting next week, Java, because it's easier, much easier. But I do have some diehard C++ people who, love C++, and they already have linked lists. They've been making linked lists for years, and they've got stacks and queues, and and they're really comfortable with dynamic memory allocation. I really love to do it that way. More than welcome to. So I want to take a quick look at the first assignment, because I did this for the other class actually earlier today. Whoops, that's Monday. We're in Wednesday. So, data structures assignment number 1. So what I did for the Java class today is I went through assignment number 1 for the Java course. I'm going to save it because it's already 3:11, and I'm going to save it and do it next week for this class. But what are we looking at? We're looking at the linked list. We just covered the concept of linked list today. So I want to talk about some of the expectations of the assignment real quick here. If I can get this to make a little bit bigger. 200%. There we go. Alright, so you're going to write a program that can be used as a database for student information for a department. So going back to students again. So the program should be able to dynamically allocate or deallocate storage of the student records using linked lists. So you must use a linked list to keep track of the list in terms of the program. That's the basic understanding of the program. If you're C++ oriented, you're probably going to do a linked list using a structure and using a class, perhaps, with nodes, and the nodes are going to be student objects. And you're going to keep track of students, you're going to stick them in a linked list, and you're going to do some basic functionality on them. That is okay to do. If you're going to take this approach and say, well, I don't like C++, I want to do this in Java, then next week I'm actually going to make the template for you. That's why I say bring your computer next week, because what I'll do is I'll show you how to import the class, and I'll put the code out on the internet so you can actually kind of see it and use it as a basis for creating yours. and you'll see how much less work it actually is. I'm only, basically doing it in Java because it's too hard to do it in C++, really. It's not too hard. I'm just too lazy. Why do it in C++? I don't know. But people learn C++. In fact, a lot of traditional computer science people, undergraduate programs, they learn C++. That's like the language everybody learns. Nobody learns Java. And then they get out and they go, well, Java, all the Android stuff's in Java, all the most of the internet development stuff's in Java. Not a bad idea to get familiar with Java. So use it as an opportunity to increase your Java skills. So the database should have the following fields. So the first and the last name, well, that's good. Course code, the grade of the student. You can use a structure if you're using C++. You don't have to. You can't do this if you're doing Java. You have to use a class if you're using Java. Or any other data type of your choice to store the information. If you don't want to use a structure, you want to do this the total hard way, don't use the structure. Just use a bunch of variables. It's going to be a lot harder in a node, class node. Don't even put students' structures in a node as a node. In fact, you can make that as more complicated as you want. If you're using a scripting language, I have had a couple people do this in Perl. You can do it. I'm not going to teach Perl in this class, though. I don't think you probably could do this in JavaScript if you wanted to, but it's really hard to create the linked list structure. Because if you think about the concept of what I just talked about today in terms of that chapter, what makes the linked list? The reference. How are you going to do a reference without memory? Without having, and scripting languages don't normally support memory references, reference structures. JavaScript actually supports reference structures. So you can actually do it in JavaScript if you wanted to. But you don't have to. You can be creative. So you're going to have a little menu that shows up. And I'll actually put this together for you next week. So you'll see it. But welcome to the database menu. You're going to have... What are these? These are going to be the operations that we're going to perform on the linked list. So the main issue is, how are you going to insert a new student? How are you going to delete a student? Searching by last name, printing the range, printing all the students in the database, finding the average, the class average for a course as an example, which a course is going to be your list perhaps. You're going to have one class and it's going to have a bunch of students in it. So don't make this extremely difficult to support multiple lists of multiple classes with multiple students. Simplify it for ease of use. The insert function should work regardless of the position. So one of the design decisions we're going to have to think about is, is it position 0? Is it the head of the list? And then if we're doing a linked structure, which we're doing in this particular assignment, then we're going to need to be concerned with how the operation is going to be different than if it's at the head position versus in the middle of the position. Any position greater than the length of the database should be put at the last position if we're going to insert something, let's say. Similarly, deleting the position should work for any position. Make sure that it works even if you're deleting the first, the middle, or the last entry in the list. And the search function should be used to search by the last name. So if the student is found, the record associated with the student should be printed to the screen. So that's kind of a trivial thing. And what do we have here? Print function should work regardless of the range requested. You'll find when you start printing it, you'll actually have to create a function to, or a method to actually print the items, which means you have to figure out how to traverse through. And traversing through next, or previous is kind of tricky when you first do it. So the purpose of it is just to have you do it at least once to do a search. Hint, to compute the class average, you first search the fields of the course and only the average for those grades that match the proper course. As I mentioned before, you can only have one course if you want. You don't have to worry about keeping track of students for multiple courses. You can make it easier on yourself. Just have one course. Implement the above program in any programming language using any technique that you want, as long as you're meeting the requirements as they're described above. This is kind of the theme of all of the assignments for this particular course. It's going to be any language you want. So And what I'm going to do next week for you is I'll spend the entire class time going over a brief yet not complete, because you're supposed to do this, implementation of this program and kind of see how the linked list differs, and we'll probably stick some arrays in there too. I'll probably do some array implementations next week as well, but at least get you started. If you're brand new to Java and you want to do this in Java, go on my YouTube site. Actually, just go into the current Java course that's in here and get your environment set up for next week. So you can, if you're in the Java class, you're already there. If you're not and you haven't ever taken the Java course and you haven't gotten Java installed, go into this course here, Object-Oriented Programming with Java, and come down to the course materials link. It's hidden in there a little bit. And you want to go into Java video tutorials, this will walk you through downloading the software, installing the Java SE, configuring your system, downloading Eclipse, installing Eclipse. Each one, it takes about a couple hours actually. And then overview and introduction to object-oriented programming. These tutorials will get you up to speed, and you'll learn Java at the same time if you haven't taken the Java course. You're not taking it now, and if you have an interest in learning Java and you want to do this, then that way you'll have your system all set up, and then next week you come in with it, and then you can install the example or download and open up the example that I'm going to create in Eclipse that you'll be able to follow along with, hopefully, and work with. So, questions, comments, concerns for today? So this class kind of came like real quickly from a beginning to now we're going to implement some data structures. So this is kind of the pattern for the next couple weeks. Is we'll go through queues next, then we'll go through some more sophisticated queues and stacks combos, and then we'll hit trees and maps and a bunch of other structures. And we just keep going through different types of data structures, all in Java. Okay, see you next time.